All right, here we go. This is the longest section of the notes, and it's all because of graphic organizers. It really isn't that long in total, but it is kind of a lot. So I'm going to get through it. I'm going to try and go through it as fast as I can. This is a ring of charge, and the main thing to understand about the ring of charge is that each point on the ring exerts electric field at point P. Okay, so not it's not just the top and the bottom. Okay, it's everywhere around it. But they're actually it's kind of funny that I say that it's not just top and bottom because you can actually approximate this as being just two single charges at the top and bottom of the ring. Okay, and the reason we're able to do that is because each side of the ring cancels out each other's electric fields. Okay, so you only really the only part that matters is these parts up here at the top. Okay, if you can think about that kind of conceptually, the parts on the sides here cancel each other out, and so you end up getting just an electric field going in the x direction. There's no y component to the electric field that ends up happening. Okay. Um, this is basically, I mean, and each of these charges, by the way, has to have a charge of Q over 2. Okay, Q over 2. So it's going to have the total charge of the ring divided by 2 because it's carrying, each charge has to carry half of the total charge of the ring. Okay. Why is it that the electric field has no components in the y and z directions? I just said it's because the opposite sides of the ring cancel each. So opposite sides of ring cancel out um, cancel out the E field, the Y and Z components. Opposite sides of the ring cancel out Y and Z components from each other. So I probably didn't explain. I probably didn't English very well there, but you get the point. Okay. The simpler arrangement is way easier to determine the electric field for, and this actually ends up being the exact same equation that we derived in the previous part. The only difference is that we're not using the same symbols. Okay, so it does end up being the exact same equation that we got earlier. I think the only difference is that there's no 2 here because the net charge is not 2. It's not 2 Q, it's 1/2 Q. Okay, so it would end up being, you should end up seeing that this would ends up driving out to being E equals K Q X naught over X naught squared plus capital R squared to the 3/2 power. Okay, we're using capital R now for it's weird, right? We're using capital R for the heights here, and then this would be lowercase r as the hypotenuse. Okay. Now, if we were to take this ring of charge, okay, and we were to go really far away from it, if x is much greater than r, okay, then x squared plus capital R squared should just equal x squared, right? And you can see that that approximation, if you plug it into there, is the exact same thing because this would just become E equals K Q X over, or I guess it would be X naught, right? Or I guess it doesn't need to be X naught. I guess it should just be X, right? KQX over x squared plus r squared to the 3/2 power. This part right here is going to end up just being x squared. Cancels out with the exponent. You get x cubed in the denominator, and it cancels the x up there. It's the exact same steps from last time, so I don't think I need to show all of that because it's just in the previous section right there, okay? KQ over x squared, okay? And then you end up with the inverse square relationship right there. So what we should see is if we graph it, okay, the electric field should start at 0 at the origin, because at the origin, all E field cancels out because you're in the middle of the ring and everything cancels out. There's no X component. And then it should gradually increase until you get to some point. So it should gradually increase to a maximum value right about here, okay? and then it will asymptotically decrease to 0. So what's going to happen is as you go, it increases to some height, and then it will go, and then it will asymptotically decrease to 0. Okay, and you notice that you have an inflection point at root 3 over 2 r. Okay. The reason why the electric field follows this behavior, okay, or the magnitude of the electric field follows this behavior, is because as as x approaches infinity, okay, E field has to approach 0, okay, because E decreases the further you get from the charges. Okay. Additionally, okay, as x approaches 0, E must also approach 0 because because since the x components get smaller. Okay. And the y components are all going to cancel out. I guess I should say because since the x maybe it just said because the x components get smaller. As you get closer to the ring, more of the electric field is going to be directed in the y direction, and it doesn't matter how much y direction electric field you have because it all is going to get canceled out anyway by the opposite sides of the ring. Okay, we talked about that in like the first point on this page. Okay. A continuous charge distribution, it just means, so you're going to hear that term quite a bit. It's just a charged object or arrangement of objects that's not shaped like a point. We've only done with point charges, but now in order to continuous charge distribution, we have to split the object into we're going to cut it up in these tiny little pieces. We're going to call them dq. Okay, we're going to find the electric field that each little piece dq exerts, and then we add up all the little de's to get a total e. And you're thinking this looks kind of like a differential equation, and that's because it kind of is, but not really, because it's actually going to look something different, like something different. This is the formula for electric field that's given to you on your formula sheet. Okay, in the calculus-based one is dE equals k dq over r squared. This gets you the tiny electric field E created by a piece, but in order for us to get the total electric field, which is just E, we need to integrate to get rid of the differential. So that's just going to be E equals the integral of k dq over, oh, let me actually rewrite this because I already wrote it so bad. E equals integral k dq over r squared. Okay, so now we're actually introducing calculus into the E&M now by integrating to get the total electric charge or total electric field produced by a continuous charge distribution. Okay. Okay. If you have an arc of charge, okay, this is the first example, is an arc of charge. This is very similar to having just a bunch of little charges at each of these points. Okay, what you're going to notice is that in figure A, you're going to have fields from right here. Okay, you're going to have a field right here, and then you'll have a field right here, right? Okay, well, the vertical components are all going to cancel out, and so you're going to end up with just this net horizontal charge. Okay, so really, if I wanted to write my expression for figure A, I could do, k q over r squared, okay, times the cosine of negative 30 degrees, okay, plus kq over r squared times the cosine of 0 degrees, okay, and then plus kq over r squared of the cosine of 30 degrees. That is not a very efficient expression. I did not use the least amount of ink or pencil lead. Okay, it's not a very efficient expression for us. Okay, but we can make it look a little bit nicer. Okay, Let me do figure B real quick. Okay, figure B. What you should notice is that the charges that are opposite each other are going to end up canceling each other out. So what we should see is that you're going to get, this charge cancels out with these ones, this one. So boom, they both erase each other. This one cancels out with this one. This one cancels out with this one. Okay. And then it says they're each separated by 30 degrees. So you'll notice that the angles here, right? This is going to be, 30 degrees, negative 30 degrees. This is going to be negative 60 degrees. This is going to be negative 120. And then this is going to be, negative 90, my bad. 90. And then this is going to be negative 120. Okay? Okay. So that's just some stuff to keep in mind. But these are basically the exact same scenario. Do you see that, right? The charges cancel out to form the exact same scenario as we had in A, right? Okay. And then if we were to do it for figure B, that would be just an absolutely excruciating expression to write. It would just be, E equals KQ over, or KQ over R squared cosine of 120 degrees plus KQ over R squared cosine of 90 degrees plus KQ over R squared of cosine of 60 degrees. And do you get the point? Like, do you see the point here? How it's just absolutely tediously boring, right? And you do all that until you get to Q over R squared of cosine times cosine of negative 120 degrees. You do that all the way through so you can get every single charge included into it. And that's just a complete mess. It's horrible. We hate it. We don't want to do it anymore. It's sad. Okay. And I guess I should have been using capital R because it tells me to use capital R in all of this. But you know what? I don't really care all that much. Okay. Did I use capital R in the previous one? Yeah, I did. So I guess I half followed the rules, right? There's an easy way to rewrite this in such a nice way so that we don't have to use nearly as much ink or pencil lead, because ink and pencil lead are expensive and we don't want to get more, okay? The easiest way to do this is I'm going to do the electric field is equal to KQ over R. Do you notice that KQ over R is constant in all of these because we have a constant charge and a constant distance, okay? And I'm going to do the sum of cosine 30 degrees times n. And I'm going to sweep from n equals negative 4 to 4. Okay, do you see how I'm just sweeping through all of the charges at this point? I've kind of written a code in a way. This is like, I always think of the sigma notation, the summation notation, as like a for loop, right? It's a for loop, right? If you take computer science, then it's a for loop, right? You establish your variable, you say that for this is less than this value, and then every time it completes the loop, you can increment it by 1, and that's exactly what we're doing right here. Okay, so we're sweeping through each charge, we're getting the cosine of each of those, and then we're multiplying it by KQ over R. Really, I mean, this is just these equations, but factored out and looking and much simpler, right? Okay, the electric field in both diagrams has the same strength at point P. Explain why this is both conceptually. Well, I mean, easily. Charges on op sides cancel each other out. Okay? So the charges on opposite sides cancel each other out. Okay? Also, know this, okay, that cosine of theta is equal to the negative cosine of that same angle plus 180. Okay? So that works out too. So again, if we look at the cosine stuff, you're going to see that we end up repeating angles a lot. Okay? And that's going to give us a lot of the same cosine values, so then it ends up or it gives us a negative value. So we'd end up getting, what we get for like one of them is going to end up showing up again as a negative later, and then it's going to cancel it out, because when we add it all up, it's going to cancel out. Okay. In each of these cases right here, something that's important to consider is that this is not a bunch of point charges at angles. This is a continuous arc of charge. And the biggest thing to consider here is that not only is it exerting field at each of the lines that it intersects through, but it's also exerting field in between those lines too, right? Okay. In case B, you're seeing the exact same thing. It's going to look very identical to what you had, at the other, and it's going to have the same stuff that you had in the previous one, but now we're adding in these slices right here. Okay, it's like a piece of pizza. It's like the cheese on the pizza, right? The cheese of the pizza is now exerting electric field that we cannot ignore. Okay, and yes, it still has these parts in here. I'm just not drawing them because I don't want it to get too cluttered. Okay. In case C, you now have electric field basically fanning out the whole way. Now, here's the thing. In case C, you actually do have a little bit of cancellation happening, but it's very, very slight. The only thing that cancels out is these very top and bottom pieces right here. Okay? But everything else does not cancel out. So when you add in, you have all the little areas that we had earlier, but you're adding in these sections, and these sections do not cancel out because they can't be canceled out yet. Okay, nothing gets canceled out in C except for the very, very top and bottom of those fields. Those literally just those arrows. Everything else stays constant. Okay. In case D, now you've got electric field basically like almost entirely encompassing your charge, or your point. And you'll notice that what happens in case D is that you don't have, the only area of charge, the only space in like the only cheese in the pizza that's applying electric field here is going to be these parts and these parts here, right here as well. Okay. Case E is even more egregious because you've now are almost entirely encircling the charge or the point. So you have so much electric field here and it all basically cancels out. Okay. It basically all cancels out. The only part that doesn't cancel out, the only area that doesn't cancel out is this little bit right here. These little bits. Okay. So do you notice that these cases are very, very similar to each other, and some of them are actually identical to each other. Okay. If I rank the strength of the electric field at point P, assuming they all have the same charge per length density, okay, then what's going to happen is you're going to notice that C is going to end up being greater than B, which will be equal to D, which is greater than A, which will be equal to E. You're going to notice that B and D are the exact same cases after all the cancellations have been made. And A and E are going to be the exact same cases after all cancellations have occurred. Okay? So you'll notice that the least electric field cancels in C. Okay? C has the most E field that doesn't cancel. Okay. And then you're going to see that D cancels down to become B. Same for E turning into A. Okay. Now, the cases, okay, and then the second part, you do have to read it carefully. It says the total charge of the rod. If they all have the same total charge of the rod, then you're actually, so they all have the same total charge. That charge distributes itself throughout the rod. You're going to notice that A is going to have a really large charge density because it's the shortest and it gets the same amount of charge as everybody. Meanwhile, in E, the charges have a lot more space to spread out and kind of fan out throughout the charges. So you're going to notice that actually as the longer the arc gets, the weaker the electric field gets because more of those charges can spread out to places where it'll end up getting canceled out, right? So we can go from A, A is greater than B, which is greater than C, which is greater than D, which is greater than E, okay? Because shorter rod, shorter arc means less room for charges to spread out. Okay. And that means less chance of them canceling each other out. Okay. So if you put, all the charge on E, it may end up distributing itself to those lower and the top parts where it ends up canceling out with the other sides. Um, and obviously that would lead to a lower strength of the electric field because some stuff gets canceled out. Okay. Okay, this is the start of the graphic organizers, which is just absolutely wonderful. Okay. Consider a arc with a curvature center at the origin. One thing that's important to note about an arc that's centered on the origin is that every single little piece of the arc is the exact same distance from the origin as each other. There's not parts of the arc that are closer to the origin than others. It's all going to be the exact same distance from the origin. Okay. Derive an expression for the linear charge density lambda of the arc in terms of q, r, and theta. Linear charge density. Okay. By the way, this is kind of a new word for you. This linear charge density is simply saying the charge per length. Okay? And if I'm thinking about the, linear charge density is charge per length, well, the total charge on it is Q. We're given that in the problem. And then the length of the arc is going to be simply the arc length formula. The whole, by the way, just to note, right? Theta is just the angle from here to here. This is theta. Or why did I draw an 8? This should be a theta. Okay. So that means that from here to here, it needs to be also theta. So it had to be 2 theta. So the whole angle of the arc is 2 theta. Okay. And if I remember that arc length is the radius times the angle, then I can do 2 r theta to get the arc length. Okay. It's the arc length, but it has to be doubled because if you just do r theta, you're just getting one piece up here. If you do both, then it sweeps through the entire arc. Okay. If Q stays constant but theta goes to pi radians, what electric field should you expect to get at the origin? Well, if theta is pi radians, that's half of the unit circle. Well, understand that it has to be 2 times theta. That's only half of the arc, right? So if this became pi radians, this is currently theta radians, but if this went up to pi radians all the way around, then the other side would also have to go all the way to pi radians. You'd have a completely closed ring, and that would have 0 E field at the center of it, okay? So I would say 0, okay, if theta equals pi radians, okay, then ring is closed and all E field cancels at center. Okay? All the E field cancels at the center of the ring. If Q stays constant but theta goes to 0, what electric field should you expect to get at the origin? Well, if theta ends up being 0, then that means that basically this is going to go right down to this distance. This will go right down to this distance. That's just a point charge. Okay. This becomes E field would be equal to KQ over R squared. Okay. And that's just a point charge. Okay. Okay. So let's fill in the graphic the organizer real quick. This helps you derive. You're not going to have it on your test, but you definitely want to kind of get used to using it because it's good in practice. You're going to choose a variable of integration. It needs to either be a length or an angle. In this case, it needs to be what's most appropriate for the problem that we're looking at. Length is not really appropriate to use because length isn't changing. What's changing, right? Angle is something that we can change really easily. So we're going to do angle. I'm going to choose my variable to be phi, okay, which is a new angle, and I'm going to have this represent the angle of a line, okay, pointing to piece DQ, okay? So we're going to basically have a line that goes from the origin and points to each of the pieces here. You see how there's a piece dq right there? We'd start here and we would point up there. And then the angle phi is that angle right there. Okay? You see how that works out? I'm going to have to sweep through the whole arc, so I want my phi to range from negative theta to positive theta. Okay? And what are the constants that are given in the problem? It's these right here, just straight up. K, Q, R, and theta. Okay, we don't want to go outside of that list. We don't have to include everything, but we don't want to go outside of that list. Okay, I'm going to use lambda at some points in here too, but you don't want that to show up in your final answer. The charge density is uniform. We're not going to get to non-uniform for a little bit, but the charge density is uniform. So I'm going to set up a ratio between d, q, and my variable, which is phi again, and solve for dq. My tiny integration variable is d phi. Okay. Tiny charge is dq. The whole charge is just capital Q. The whole integration variable, the whole angle that I'm integrating through, is just 2 theta. Okay. So this becomes q. If I solve for dq, I just multiply d phi on both sides. So this becomes q over 2 theta times d phi. So now I can replace dq with this expression right here in my actual integral. Okay. So then the distance from each piece to the point of interest P, it's going to be the same because it's an arc of charge, right? It's going to be the exact same because it's an arc of charge. So arc of charge, every piece is the same distance from the origin or whatever. And so my expression is just going to be capital R, right? That's the distance that every single piece is from there. It's the radius, okay? And then as I go, do I have to deal with components? Because it's an arc of charge and the angle is changing, yes. So most typically, if you're dealing with angles and you're dealing with arcs, you will have to, well, if you're dealing with arcs, you definitely have to deal with components because only one component actually has an effect on it. It's the x component in this case, so we're going to use cosine, okay? Only x component, okay? An expression for the component maker in terms of the constants and the variable, that's phi. Phi is my variable again. I'm going to use my trig function. So I'm just building it together. I'm not having to really do any real thinking here. I'm literally just piecing everything together. Cosine of phi is equal to, and you're not going to believe this, cosine of phi. Okay, that's what I'm just going to use for that. Okay. Okay. Now I've got all my pieces. I just need to build my integral now. That's the last thing I need to do. So I'm just going to put everything that I've said into here. Okay, that's all I have to do at this point. My lower limit is going to be phi equals negative theta, and my upper limit is going to be phi equals positive theta. Okay. My expression for dq I got earlier is q over 2 theta times d phi. And then my expression for the distance r was capital R. My component maker is up here. Okay, that's cosine phi. When I simplify my integral, I can pull any constants out, anything that's not in terms of theta, or sorry, anything that's not in terms of phi, which is basically going to be everything except for cosine. So this really just becomes kq over 2 theta r squared times cosine phi d phi. Okay, and I need to apply my bounds too. This goes from negative theta to positive theta. Okay. When I evaluate the integral, okay, well, the integral of cosine is going to be sine. Okay, so let me find, or which pen did I want to use? I was going to use, let's use this one. Okay, well, I guess I should use the same color, right? The constants are still going to be k, q over 2 theta r squared. The integrated expression is simply going to be sine of phi, and they still go from negative theta to positive theta. Okay. So then what ends up happening is I plug in my bounds. I end up getting, and I should end up seeing that this becomes KQ over 2 theta r squared. And this ends up becoming, so this would just really quickly, as like a little bit of a side, you should see that this becomes sine theta minus, or sorry, plus sine of negative theta. Okay. And this ends up becoming sine theta plus sine theta. This should be, or sorry, it should be minus. Where's my, I don't have like my whiteout with me. It should be minus, right? And then this ends up becoming plus sine of theta. Okay. So this really is just 2 sine theta. Okay. This is going to be 2 sine theta. Okay. And you can cancel out your 2's because you have a 2 in the top, 2 in the bottom. And this really is just going to become KQ over r squared times sine theta over theta. Okay, that's all you have to do for that. Okay. Okay. That's all you have to do for that, to solve that integral out, right? So there we go. We integrated it. We solved it. We did good. Okay. The next one, I believe it tells you to do page 18 first before you start that page. Okay, so I'm going to go to page 18 real quick, and you're going to see like everything that we're going to do here. I don't know why page 18 doesn't just like come first. Okay. This is like a train of charges or a uniform line of charges. Okay. And the way that the uniform line of charges works is that you have each charge is a different distance from P. So you actually, in this case, are going to have to integrate using that. So the expression I'm going to use for this is I'm actually going to use the summation notation for this. Okay, I'm going to label each charge, 0, 1, 2, 3, 4, 5. Okay. And what I'm going to do is I'm going to sweep from n equals 0 to 5, okay? And I'm going to do KQ, that's going to be constant, that never changes. And then the distance, what's the distance from point P? Well, the whole distance is A and minus D, but obviously notice that like 1 has distance D right here. Notice that 2 has distance D plus distance D. Oh, so 2D. So I can just do A minus ND squared. Okay, that's my expression for the uniform line of charge. Okay, and now it says suppose that the charges had different values and the values depend on where the charge was located, specifically that Q is equal to BX squared. What's a new expression for the electric field? Well, I'd have to say, okay, Q is equal to BX squared. Okay. Well, I already said that x, the distance, is simply going to be b, n times d, okay, because that's the distance where it is, right, squared, okay, and you can expand this out to be b n squared d squared. That's fine too, all right. And so now what I can do is I can replace this for Q in the previous equation. So I would simply just do E equals the epsilon, or sigma n equals 0 to 5, okay, k times b n squared d squared over a minus n d squared. And you don't have to simplify any more than that. I'm actually completely fine with this. Okay, I did not simplify any more than that because I did not want to. And I am the teacher. And I get to say that if I don't want to do it, I don't have to do it. Okay, I already got my degree. Okay, so I'm not going to simplify that anymore. You could FOIL this on the bottom if you wanted to. I don't recommend it because it's dumb. Okay, I don't recommend it because I'm never going to ask you to simplify things on a test or anything unless I'm. If I do that, then the aliens have harvested my brain already. In each of the cases above, there's a rod carrying a uniformly distributed positive charge and there's a point P. Rank the cases based on the electric field strength at P and explain your reasoning in these two cases. Okay, The rods have the same total charge. Okay, so if they have the same total charge, okay, then the charge equally distributes itself on the rod. Now here's the thing, okay? Notice that in case, in by default, okay, in case A, you have this much length of rod, okay? In case B, you have the same amount of length of rod, but you also have a little chunk added onto it that's further away from P. In case C, you have the same length of rod as earlier, okay? But now you have a little chunk added to it that's closer to P, okay? If the charges equally distribute themselves on the rod, then you're going to notice that C, they have more room to go closer to P. B, they have more room to go further from it. And A is, all going to be at, it's not really going to be in the middle. It's going to be kind of in the middle. Okay. So I would say that it goes C, A, B. Okay. Because in C, charges have more room to go closer to P, and in B, they can go further from P. Okay, and then A is just kind of in the middle. Okay, because it doesn't get any charges closer, but it doesn't get them any further. Okay, if they have the same linear charge density, okay, then it's again going to matter based on it's the ranking is going to look very similar. The main difference is that what's going to happen is you're going to focus more on which charges are closer. So it's length and its length, and it matters about the distance. So the longer rods are going to exert more field in general, and the closer they are, the more field they exert too. So we can say that this is actually going to be C, B, and then A. Okay. Because C is longer and closer to P, so E field goes up. Okay. B is longer but further from P, so E field goes up. And then A, I don't really need to prove A because I've already kind of implied that A is going to be last place through what I've already said. But A is shortest. So E is, or E from, I guess, B is greater than A is what I should say. E from A. Okay. A is shortest, so E must be least. Okay. Okay. Now we got to flip back to that page that we were just on, the one that told us go back to page 18 and go to page 18 and do that one. Okay. I'll be impressed if I can do this all in one video without taking a break. I consider taking a break after this one, but I'm kind of feeling it right now, so I might just truck it through, right? Okay. Okay, a rod of length L and uniform charge density lambda is set along the x-axis, so now this does have a charge density. Write an expression for the total charge on the rod. Well, charge density is, lambda equals the charge per length, right? Well, all I got to do is rearrange that, and I can get charge is equal to lambda times L. That's it. That's all I have to do for that. Okay? There's no complicated derivations, no silliness going on here. It's just lambda times L. That should make sense because lambda is going to be coulombs per meter, and L is going to be meters, so the result is going to be coulombs. Okay? Okay. Choose a variable integration. The variable should be a length or angle. The variable should point. In this case, it's most appropriate to use a length. Okay? So I'm going to use my variable is going to be x, and that's going to represent the x coordinate of each piece. dq. Okay? And to sweep through the whole rod, I need to go from the x coordinate of 0, the origin, all the way to where L is. Okay, so I'm going to go from x equals 0 to x equals L. And then what I'm given, what I can use is K, A, L, and lambda. Okay, you're gonna see me probably use Q in here at one point as well, but we don't need to list that because it's not what we need our answer to be in terms of. The charge density is uniform. Okay, so we'll go down the uniform path. We haven't done non-uniform yet. I think that's going to be more of like a Gauss's law thing. Okay. We're going to set up a ratio between dq and dx. Okay. So my tiny integration variable is dx, and then the whole charge. I already got that whole charge expression earlier. That's just q. Is lambda L. Okay. And the whole integration variable is, of course, the distance L. Hopefully you notice that L and L will just cancel out because there's one on the top, one on the bottom. So you end up with dq over dx equals lambda. And then when you solve for dq, you just get lambda dx. Okay, that's all you have to do for that. It's not a terribly. I hope it's not terribly. I hope you understand that is what I'm trying to say. Okay. The distance from each piece to the point of interest P is going to be different. So this is actually going to where it differs from the ring is that it's going to be different. Okay. Or the arc, I mean, sorry. Though consider the one piece. I always consider the one piece, right? It's real. Okay. That is at location X. Okay. And write an expression for the distance R it has from P. Okay. Well, if I look back up at the problem, this whole thing is a distance A. Okay. So why don't I just take A minus the X coordinate of the piece, wherever I am along the rod. Okay. So that's just going to be A minus X. Okay. Okay. Continuing on. Do we have to deal with components? Here's the best part about the rod is that we do not have to deal with components. Now, if the rod was vertical, we would have to deal with components, but it's not, so we don't have to deal with it. Okay? Awesome. Cool. Great. Okay? We'll just leave components blank below, and I'm okay with that, right? I'm okay with that. Okay? Now we just got to put everything all together. We throw it into the integral. We've already solved everything. We just got to put it all together in the integral. X equals L. We're going from 0 to L. Okay. Expression for dq is lambda dx. Okay. Expression for the distance r is a minus x. And we don't need a component maker because we're just cool like that. Okay. Oh, I put an x, but I don't want you to think that that's like the variable x. So I'm going to put a circle around it because, that's like, okay. All right. To simplify my integral, I'm going to pull my constants out. So anything that's not in terms of x. K and lambda are not in terms of x. Okay. Now, when I'm going to have to pull out a negative as well, and the reason for that is because I'm going to do u substitution. Okay. So I would do that u is going to be equal to a minus x. Okay. And then du would have to be equal to negative dx. Okay. And so then that would end up giving me negative k lambda integral of u to the negative second power du, and then I can integrate that really easily. Okay, so it end up being k lambda times u to the negative 1 power. I'm skipping ahead a little bit. I'm getting a little bit ahead of myself because we haven't evaluated it, but I'm telling you why that negative is going to be there. Okay. This goes from 0 to L, negative dx over a minus x squared. Okay. So again, like I said, u substitution. That's kind of what's happening between here and here. Is I'm doing u substitution in here and then solving it when I evaluate my integral. And when I do evaluate it, okay, I should get k lambda times 1 over a minus x. Okay. L from 0 to L. Okay. And when I apply my bounds, this just becomes k lambda 1 over a minus L minus 1 over a. And I do not need to simplify it any more than that. That is perfectly acceptable for my answer. Okay. Let's see. How many more pages do I have here? I've got 1, 2, 3. I think I can. I can do this. I can do it. I'm just gonna go through. I'm gonna do the whole section in the video. And you know what? If you're sad that the video is so long, I'm sorry. Okay. This is a non-uniform line of charge, so we're finally getting into the non-uniform. Oh, that's funny. I just said it was like Gauss's law, but no, it's right here, right? I keep forgetting. This is this has a non-uniform linear charge density, so that it does vary with the distance with your position on the rod. Okay, it's lambda x equals a over x squared. State the units of a. Okay, well, if I know that lambda has to be coulombs over meters. Okay, then I can do that coulombs over meters has to equal whatever A is. I don't know what A is. And then the x squared is going to be meters squared. Okay, so what I need to do is I need to cancel out one of the meters in the denominator, and then I need to add a coulombs in here. So this would have to be that A would have to be in units of coulombs times meters to cancel out. Okay, it had to be coulombs times meters because the m's would cancel out. So you don't have an m in the numerator, and you'd only have one in the denominator, and then c in the top. Okay. Okay, that's just kind of a little exercise. You do that in the performance task, or you did that in the performance task, because at least by the time I made this in 2025, the performance task was already due at this point. Sorry. Okay. Driving expression for the total charge on the rod in terms of A and L. Okay. In order to find the total charge on the rod, you actually have to integrate. So I can do, Q is equal to the integral of dq. Okay. Now, what I can do here, and I'm going to do some kind of silly stuff here, is I can multiply both sides by 1. And 1 can take many forms. It can be 2 over 2 or 3 over 3, or it could be dx over dx. Okay. And doesn't matter. And this would actually just end up becoming dq over dx times dx. Okay, so this would really just be q equals the integral of dq over dx times dx. Okay, and dq over dx, by the way, is your charge density. Okay, let me write that up here. dq over dx is charge density. So really, you just want to integrate your charge density with respect to x, and that's going to be the best way to do it. Okay. This rod, it says it's infinitely long. Does it say? Yeah, it says extremely long, which means infinitely long. Okay. So it starts at L and goes all the way to infinity. So I'm going to integrate from L to infinity. Okay. I'm going to go from L to infinity. Okay. And I'm going to do lambda dx. And then I just got to plug in my lambda. Q equals L to infinity. Lambda is going to be a x to the negative 2 power dx. Okay. And I wrote it as a power just to make life really easy for me. Okay. When I integrate this, I end up getting negative ax to the negative 1 power from L to infinity. Okay. And then when you apply your bounds, you end up getting a over infinity minus a over L. Okay, or I guess it would actually be minus negative, and it should be negatives right there too. And this actually just, a over infinity, that's just going to turn into 0, because if you have a slices of pizza and you have infinite friends to divide them in between, you're going to have 0 slices. Nobody's getting any pizza, right? So this is going to be negative or minus negative a over L, which is just going to be positive a over L. Okay. And there you go. And that should hopefully make sense too. If you look at the units of this, this is coulombs times meters over meters, and then those will cancel out, so you get coulombs, and that makes sense. Okay. That's kind of one way to check yourself. Choose a variable of integration. It should be a length or an angle. Because this is a rod, it's going to be most appropriate for us to use a length. So I'm going to use x as my length, and that represents the x coordinate, okay, of each piece dq. Okay. The variable is going to range from x equals L to x equals infinity. Okay. And the letters, it tells me, is a, k, and l. A, k, and l. Okay. Okay. In this case, we do have to go the non-uniform route, which only just adds one additional step to us. So the non-uniform charge is going to be this way. dq is simply going to be the density function, okay? And that's going to be a x to the negative second power, okay, to dx, okay? You're supposed to integrate this. I've already integrated it, so I saved myself a little bit of trouble there, okay? The distance from each piece to the point of interest P, okay? Because it's a rod, it's going to have a different distance each time, okay? So again, we're going to consider the one piece that's at location X and write an expression for the distance R it has from P, okay? We're just going to say that that's just going to be equal to X, because if you notice our point P, oh sorry, you can't see that. If you notice our point P is at the origin, so why don't I just use the X coordinate of the piece, which I've already defined as my variable of integration, or my variable of integration X, right? So why don't I just use X as that? That's the easiest way to do it, okay? Okay, so then I would continue along the path. Do I have to deal with components? Thankfully, no components here. Okay, and now I got to put the whole integral together. Okay, we're bringing the band back together. Okay, I've already said I'm going to go from L to infinity. Okay, the expression for dq was ax to the negative second power dx. The expression for r we already said was x, and we do not need any components. Okay, no components whatsoever. When I simplify my integral, okay, you'll notice that this, by the way, x to the negative 2, this is also x to the negative 2, so they can multiply together to give you x to the negative 4. So this is going to be ka, those are my constants that I pull out, and then this is going to be x to the negative 4 power dx, okay? My bounds are from L to infinity, okay? Now, all I need to do is integrate that, which is super easy to do, okay? I get negative ka over 3, and this becomes x to the negative 3. I factored out that 1/3, okay, which you can do is fine, okay, because the only thing that changes is x. So you go from L to infinity. Okay, now when I plug in my bounds, this is going to end up being negative ka over 3 infinity squared, okay, or sorry, cubed. And then we subtract from that negative ka over 3l cubed. And you're going to notice again that right here, if you have ka slices of pizza and you want to divide them amongst 3 times infinity to the cubed friends, nobody's going to get any pizza because you don't have enough for that many pizza people. Infinitely many friends means you're splitting pizza amongst infinitely many people, which just cannot happen. So this becomes 0, okay? So the solution, this is minus negative, so this ends up becoming E equals Ka over 3L squared. Okay? Okay. So there's that one. This is now like the vertical line of charges, which we've kind of teased a little bit. We talked very briefly about it. Okay? If you have a vertical line of charges, okay, then the way that you can do this is that instead when you write the summation, instead of sweeping through the x positions of each one, you have to sweep through the vertical positions of each one. So what I'm going to do is I'm going to say that this is basically the same thing as the vertical 2 charges. The y components cancel out, so I'm only concerned about the x components. Okay, kq over r squared, okay, times, what I can do is I need the cosine, okay, because it's the x component. Well, I'm just going to do the cosine, which is going to be the adjacent over hypotenuse. That's going to be b over r, okay? R is going to be, r would have to be equal to the y squared plus b squared to the 1/2 power, okay? When you multiply this together, this becomes r cubed, okay? which is going to give us e to the e sub x is going to be equal to k q b over r cubed, which is just y squared plus b squared to the 3/2 power. Okay. And what you would do is you would have to, now you could write this in summation notation. Okay. So to get the net charge, that's just the x component of the charge. To get the net charge, you have to then take this expression and add it for each individual charge. Okay. So I can do, this is going to be n equals, I'm going to number these, okay, 0, 1, 2, -1, -2. You could you could do, I think, from like 0 to 4 if you, 0, 1, 2, 3, 4 if you wanted to. You can do it however you want, okay? It should end up giving you about the same expression either way, or it might be a little bit different. I'm going to start at -2, and then I'm going to go all the way up to 2, because I'm going to sweep through every single charge. This is going to be KQB over, now y does have to change because y is changing as we go. If each one is a distance d above this, then I'm going to do n times d, okay? N d, okay, squared plus b squared to the 3/2 power, okay? So there you go. That is that's the summation notation form of that, okay? Now, we haven't integrated yet because that's not a continuous. This is now continuous charge continuous charge distribution right here, which is a vertical rod. This does have, right, this one, the vertical rod, it is a little bit different. It's very similar, but it's different. It wants you to use it mentions using a cast tool to evaluate the integral. And you can do that. A lot of the integrals that we do in class and stuff like that, some of the more challenging ones, you can use a cast tool, but on the test, you're not going to have a cast tool unless you have one on like a TI Inspire. You're not going to have access to like the Symbolab Definite Integral Calculator or integralcalculator.com. So there's that. Okay. Determine the electric field strength at a point x equals x naught on the x-axis. It actually should say b. It should be a point x equals b because you've got you're at a distance b from there. Okay, so there's a little error right there. It should be x equals b on the x-axis. Use the organizer to construct your integral and use a cast tool. Okay, so let's construct it. I'm going to choose my length as being my variable. I'm going to choose my variable being y, okay, which represents the y coordinate of each piece, okay? This variable has to range from -a, because it says in the problem -a is the lower bound and upper a is or positive a is the upper bound, okay? Write the letters of all constants that are given in the problem. It tells us to do it in terms of, it doesn't actually give us our list of variables here. So we're going to use K, there's just constant A, we're going to use B, and we're going to use lambda. Okay, those are going to be the ones that we stick with. Okay. Charge density in this case is uniform. So we're going to go with the uniform path, thankfully, because the uniform path is a little bit easier to do. Okay. We're doing dy. The tiny integration variable, okay, is dy. The whole charge is q, and the whole integration variable is the length of the whole rod, which would be 2a, right? Wait a minute. Q over 2a is charge over the whole length, which is charge density. Right? So this is actually equal to lambda. So I can just say that this is lambda. I don't even care about this part right here. I just going to say that's lambda because it makes my life easy. This is going to be lambda dy. Okay? The distance from each point piece to the point of interest in this case is going to be different. You might be tempted to say that it's the same, but that was only the case for the arc. In this case, it's different. The reason is because as you go, right, the y component of the x component of the triangle is staying the same. Y component is increasing, so the hypotenuse is also going to change as well. Okay, so the distance is going to change. Consider the one piece that is at a location, we're going to call it y, okay, because that's our variable, and write an expression for the distance r it has from P. Well, we already got that expression. We're just using the Pythagorean theorem. B squared plus y squared to the 1/2 power. Okay? Okay. Do we have to deal with components? Unfortunately, yes, this is a case in where we do have to deal with components, which is very sad. But thankfully, there's no x components. We know it's y component. Or sorry, we know it's only x components, right? So we have to use cosine. Okay. Okay. An expression for the component maker in terms of constants and y. Okay. I can say that the cosine of the angle, which is theta, I want to get it in terms of y. Okay. So I don't want to leave it just cosine theta like I did that one time. I actually have to get it in terms of y. I can actually express this as being the adjacent over hypotenuse, which would be b over r, which in this case is going to be equal to b over y squared plus b squared to the 1/2 power. Okay. I can do that. That's fine. I'm fine with that. Okay. And now when I build my integral, when I put everything together, it's going to end up so wonderful and serendipitous. Okay. I don't have anything in, so my limits, right? I need to go from negative a to positive a. Okay. For my expression for dq, I got lambda dq, lambda dy, sorry, not lambda dq. The expression for the distance r is y squared plus b squared to the 1/2 power. My component maker is what I wrote up here, b over y squared plus b squared to the 1/2 power. And then to simplify my integral, this is going to be a huge mess. Like, do you notice that we've got so much stuff going on here with y and all that fun stuff, and it's just going to be a complete mess, right? So at this point, you put it into the cast tool, right? If I simplify my integral real quick, I can pull my constants out. So I should get k lambda b from negative a to positive a. The integrand, what I'm going to be integrating is going to be dy on the top, and then I'm going to have y squared plus b squared to the 3/2 power, because I can combine these two right here. Okay. And then the differential is going to be, oh, I already got the differential. It's dy right there. Okay. Okay. Now this is where you plug it into the cast tool. Okay. And when I did that, okay, you're gonna have to trust me that I did that, okay, because I'm not going to show it to you here. When you plug it into the cast, you're going to get k lambda b, okay, times your integrated expression, which ends up being y over b squared root y squared plus b squared, and I'm applying my limits negative a to positive a, okay. Okay, and again, I'd use the cast tool. So if you do the definite integral calculator, or even if you use integrate, you just Google integral calculator and you get the first thing that pops up, then you will see that it'll actually solve the definite integral for you too. And when it simplifies out, I end up getting it ends up being 2k lambda ba over b squared root b squared plus a squared. Okay, it ends up being a complete mess of an integral to solve, but that's what you end up getting when you plug that in. That's all through the cast tool. That's all through an integral calculator. Now, if electric field, so if B becomes much larger than A, then what you're going to notice, okay, is that this whole thing is going to turn into B, this whole thing on the bottom here. So let's see, if B becomes much larger than A, then you're going to notice that what happens down here is that B squared plus A squared is going to just become B squared. And then you get the root B squared. Well, a couple things to, actually, let me just rewrite it out here for you. if you look at the equation as it stands right now, 2k lambda ba over b squared root b squared plus a squared, then you're going to notice a couple of things. First off is that your b's can cancel out. And so you're left with one b down there. Well, if let me say if b is much greater than a, then you know, b squared plus a squared equals b squared. Okay? So then this would become E equals 2k lambda a over b times root b squared. And then that becomes just b multiplied by b gives you b squared. So this would actually just end up becoming 2k lambda a over b squared. And that is the beautiful inverse square law that we've been looking for. Okay, so that works out. Okay, it's expected because it has a inverse square law. Okay, if A is much larger than B, okay, this is the near field approximation. If A is much larger than B, then you would see that what happens is you get E equals 2k lambda BA over B squared times root A squared. Okay, you would get these B's cancel out still. And then root A squared is going to cancel, is going to give you just A, and then the A's will cancel out up here. So then you would just get the E equals 2kx over B. Okay, and it's just inversely proportional. Okay, there is no inverse square law that happens there. It's just inversely proportional. Okay. Oh my gosh, I did it all in one video, and if it doesn't upload, I'm going to crash out. Okay, all right, peace out, have fun. I'll see you in the next one.